Alrighty, let's get started here today. We need to wrap up a couple things from last time and then talk a little bit about energy transfer, phase change, and how we can represent that and solve some problems. And then we will finish today working on that packet that says enthalpy of and a couple of Edpuzzles that go with it. So look in your folder and find our sheet from last time, which started with this energy, heating, and cooling thing. We're basically done with this. We just had one more idea that we need to talk about here, which was the heat of fusion and heat of vaporization. The heat of fusion was actually the thing that caused us problems when we got to part 4 of the specifics of temperature change. It caused us the issues with the water getting colder than we thought it should because it took some of the energy out of the water in order to get the ice to melt before we could even start bringing the melted water up to temperature. The heat of fusion is the energy required to melt 1 mole of substance at the melting point. And just like specific heat is unique to each substance, the amount of energy it takes to melt something is unique to each substance. On your resource sheet for the unit, you have the heat of fusion of water listed there. So it tells you on your resource sheet how much energy it takes to melt ice. But if you needed to melt something else, like melt aluminum, the energy it takes to melt a mole of aluminum is going to be different than the amount of energy it takes to melt 1 mole of ice. The partner process is heat of vaporization. Heat of vaporization is the energy required to vaporize one mole of substance at the boiling point. Now, if you look at your resource sheet, you will see that for water, we have 3 different specific heats: the specific heat of ice, the specific heat of water, and the specific heat of steam. And you have a heat of fusion, and you have a heat of vaporization. That means that if you wanted to completely describe the process of taking ice from somewhere below the freezing point all the way up to steam somewhere above the boiling point, it would take 5 different equations and 5 different physical constants to get this done. And I'm going to draw that and put all the parts and pieces in place for you. You may want to sketch this on a piece of paper. I think the back of that enthalpy packet actually might be blank if you want to put it there, or if you want to put it on another piece of paper, that's fine as well. Class. The draw here. Not ideal. Set the pen. In our last class, I set up a little demonstration. And we actually took measurements here. What the heck? Pen tray has an issue. Smartboard not working ideally today. We actually had the experiment graph for us. The temperature of our sample versus time, but time was a way for us to measure how much energy had gone into our system. We set the hot plate up, I turned it to a constant level, and then we just kind of assumed that there was a steady state of energy going into this thing. So we could think of this axis as actually having been the energy axis as well. And we started with ice at a temperature somewhere below zero. And the temperature went up, up, up for a while. And then once we hit 0 degrees Celsius, we ended up kind of having a plateau. Like, while the ice was melting, the temperature didn't go up. But then once the ice was melted, the temperature went up, 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 and then it leveled off. And that was the end of what we were capable of doing with the equipment that we had set up, because once it hit the boiling point, any water that vaporized actually left my beaker, and I had no way to further heat it. But if I had caught the steam and continued to heat the steam, this would have gone up, up, up again. And our plateau here was at 100 degrees Celsius, which is the boiling point of water. Every substance has a heating-cooling curve that looks like this. The only difference is that the melting point and boiling point are at different temperatures along the way. The width of these plateaus changes a little bit, and the slope of the hills changes a little bit. But this is the general process of heating something from below its freezing point up to a temperature above its boiling point. If we have to describe how much energy is transferred at each of these points along the way, as you come up this slope right here, in the case of water, this is going to be energy transferred to go up the slope is the specific heat for the solid, which in the case for water is going to be the specific heat for ice, times the mass, times the change in temperature for the time that it's a solid. So that's our original equation. If we need to come up this little slope, the energy to come up this little slope is going to be the specific heat for the liquid state times the mass times the change in temperature over the range that it's in its liquid state. And up here on the last slope, a little more space, Q is going to be the specific heat for the gas, or the vapor, times the mass, times the change in temperature over the time that the substance is in the gaseous phase. The other piece we have now added is that we have to account for the energy it takes to cross the plateau. We can't just string these three pieces together, because we learned in our last class that melting ice doesn't behave just as if it's warming up. It's got this other behavior which is a function of melting. The energy it takes to melt something is the number of moles of substance you have times the heat of fusion. The only reason this one has to be done in number of moles is that if you look on your resource sheet, you'll see that the heat of fusion is given in terms of kilojoules per mole, as opposed to being given in terms of gram or joules per gram. If you're freezing it, we have to remove energy, which is basically to remove, so there's a negative sign, energy equivalent to the number of moles times the heat of fusion. So it's the same equation, it's just that energy is coming out instead of going in. The Q equals specific heat mass delta T equations, the positive negative takes care of itself, because the delta T can be either positive or negative. But if you're going across the melting freezing slope, you need to specify, is it energy going in or energy coming out? The same thing's true up here. The energy it takes to boil is the number of moles times delta H of vaporization. And if it's condensing, it's the opposite of the number of moles times the heat of vaporization. If you're moving this direction along the chart, Q is positive because energy is going into the system. If you're moving this direction, Q is going to be negative because you're coming down the whole thing. That is probably the best visual guide you have at this point in terms of how can you best describe everything we've accomplished in the last week and a half. Well, you can describe it by looking at that little setup and saying, okay, all I got to do is figure out where I am on this thing, and then I'll know what equation describes my situation. If I'm traversing a few different points, it's going to take a few different equations to describe my situation. So now let's take that and try to put that in context with our LOL diagrams. So here we have an energy profile curve, which is what we just, or not an energy profile curve, a heating cooling curve, which is this little thing. This shows the entire process. We can also then show, in terms of what's happening here, how this would shake out on an energy flow diagram, and also how this would shake out in terms of bar charts. So if I want to describe this little adventure, I am starting right here. I am ice at 0 degrees Celsius. Water at 0 degrees Celsius is on the other side of the plateau. So I'm in the solid state. So my initial condition is that I have 1 block of phase energy, because we decided that we'd go with 1 block for solid, 2 blocks for liquid, and 4 blocks for gas, just to signify that gases have a much, much different amount of phase energy than liquids. And I'm pretty cold. I'm at 0 degrees Celsius. So I might call that 1 block of energy. The ice is going to melt. I'm going to increase in temperature, and we're going to get all the way to the boiling point. In order for that to occur, energy has to flow into my system. And at the final point over here, I am in the gaseous phase because I'm on the far side of the plateau, which means my phase energy is now 4 blocks tall. And I've gone from 0 to 100 degrees. I have quite a lot more thermal energy. I don't care how many blocks you decide to use to represent that. Just a big enough stack to represent that the thermal energy account has gotten quite full because the temperature has gotten quite high. I would like you to take a few minutes with your team and fill in charts 2, 3, and 4. See if you can describe, oh wait, we forgot one part. Constants or delta H values that are going to be needed. Okay. So here we are going to need delta H of fusion. We're going to need the specific heat for water. And we're going to need delta H of vaporization. Where the heat of fusion gets us along here, the specific heat of water gets us up the slope, and the delta H of vaporization moves us along there. Okay, work with your team and fill in the rest of those. Okay, let's see how we did here. In number 2, we appear to have a piece of ice that's very cold, getting ever so slightly less cold. So solids have 1 block of energy stored in the phase account. It remains a solid the entire time. It just gets a little bit more energy pushed into its thermal energy account. Energy flow is into the system. The only constant I will need here is the specific heat of the ice. So not very much change going on there. This next one, we were given this situation and had to figure out what was going on. So I started here actually by looking at how much is stored in the phase account first. So I decided initially with 2 blocks, I was in the liquid state. And I had quite a bit of thermal energy, so I said I was in a liquid, warmish. And exactly where you decided to put this point, I don't think there's enough information to say exactly where. You could have put it up at 100. You could have really put it anywhere in between. But what we know is that it's a liquid. And so this much thermal energy is not more than whatever the boiling point is. In the end, we're going to be a solid because we have 1 block of phase energy, and it's going to be relatively cold. But again, we don't exactly know how cold. I think there's a couple possible answers to this one. I'm positive energy is flowing out. So I started up here. I went down to the freezing point. I froze this. What I don't know is if I went on down or not. So we don't know if we went down below being a solid. If you decided we went below being a solid, you would also need the specific heat of ice. If you decided that this was just a solid sufficiently far enough to have frozen but not dropped in temperature at all, you wouldn't include these 2 pieces that are in green. So you had a decision to make. As long as you made it for some rational reason, then you're just fine. At number 4, we were back to being given the heat and cooling curve again. I'm starting in the gaseous phase, that's 4 blocks tall, with a lot of thermal energy. It doesn't matter how high you build your stack, but just build it high so it looks really hot. And I'm going to end in the solid state. Down here, I've come down to being a solid, so down to only 1 block of phase energy. It's cold, don't know how cold, but the thermal energy account has been in some way depleted. And so I figure to track this, energy has to go out. I need the specific heat of steam, the heat of vaporization to get across this plateau right here, the specific heat of water to come down there, and the heat of fusion all has to be removed in order to come out. Yeah?
Why would we need sea ice?
Oh, I guess we don't. Oh, here? We don't need sea ice here. Up on this one, if you decided that this much thermal energy was colder than the ice just being frozen, you would need it. But if you decided this was only enough thermal energy removed to get it frozen, you wouldn't need it. So it kind of depended on how you made the decision on that one. Just make sure that it's consistent with however you made your decision. Okay, on the back here, we're going to try some qualitative problems just to get kind of an approach for how to go about doing this. So number 1 asks, how much, we probably need the word energy, how much energy would be needed to vaporize 25 grams of water after it has reached 100 degrees Celsius? So the first thing to do is to try to draw in what has gone on. So we have 25 grams of water. It is at 100 degrees to start, but it's in water state and we need to get it to vaporize. So we just want to cross that plateau. We just need enough energy to get across the plateau. We're not changing the temperature. 100 degrees is pretty hot, so we'll build ourselves a fairly hefty stack of energy in the thermal account. But the stacks are equally tall, even though my drawing is horrible. And we're going from the liquid state, which is 2 blocks stored in the phase account, to the gaseous state, which is 4 blocks. And in order to get this to happen, I have to put energy into the system. And I'm just going to make myself a note here that when I get done, Q has to be positive. I am depositing energy into my bank account. So whatever I come up with for an answer here is going to have to be positive. The physical constant needed to cross this plateau is heat of vaporization. So I'm going to need to get my resource sheet here. And on my resource sheet, here's my heat of vaporization, 40.7 kilojoules per mole. So the energy required here is going to be the number of moles that I have times delta H of vaporization. And I just looked up delta H of vaporization to be 40.7 kilojoules per mole. So I'm going to have to figure out how much is 25 grams of water. 25 grams. Need molar mass of water. Calculator here. .08 times 2 plus 15.999. 18.015 grams is 1 mole of water. Three significant figures in that 25.0. So I have 1.38 moles of water. If it takes 40.7 kilojoules to vaporize 1 mole of water, it's going to take more than 40.7 kilojoules to vaporize 1.38 moles of water. Q is going to be equal to 1.38 moles times what it takes to vaporize it, 40.7 kilojoules for every mole. It's going to take 56.2 kilojoules to vaporize that water. And we're going to be stuck at 100 degrees until that 56.2 kilojoules has been applied to the system. That's the simplest variety. One segment of the graph needs to be traversed. Number 2, how much energy would be required to turn 50 grams of water at 21 degrees into steam at 100 degrees? So water at 21 degrees is going to be about right there on my chart. And I need to end up as steam at 100. So I have to heat up the water, and then I have to apply enough energy to completely vaporize it. In order to do that, energy's got to go in. My Q is going to have to come out as a positive number. I am going from the liquid state to the gaseous state. So I'm moving energy into the phase account. And I started at about 21 degrees. And I'm going to end with a little more energy in my thermal account as I took that all the way up to 100 degrees. The rule here for doing this is however many segments you have on your graph, that's how many equations it's going to take to get the calculation done. So I need to come up the hill which is going to be the specific heat for water, and cross the plateau, which is going to be the heat of vaporization. We know this is 40.7 kilojoules per mole. And the specific heat of water, at this point, you're probably close to having that accidentally memorized. 4.184 joules per gram degree Celsius. The energy it takes to heat the water is going to be the specific heat for the water times the mass times the change in temperature. And we'll call this other one Q boil. The energy it takes to boil it is going to be the number of moles times the delta H of vaporization. So we have specific heat of water, 4.184 joules per gram degree Celsius, times the mass, 50.0 grams, times the change in temperature to get us from 21 degrees up to 100 degrees. And both of those are out to the tenths place, 79.0 degrees Celsius. So we end up having kind of a biggish number here. Keeping three significant figures, 165.00 or 16,500 joules to get up that hill. To cross the plateau, we're going to need to know how many moles of water we have. So we can do this again. 50.0 grams. 1 mole, 18.015 grams. Should be twice as much as we had before. .78 moles. So to boil it, we know how much it takes to boil 1 mole. We just have to upscale. And keeping three significant figures, 113 kilojoules. Q for the whole process is the sum of these two numbers, but we have to put them into the same unit system first. So we're going to have to divide this one by 1,000 before we can do anything with it, because we can't add joules and kilojoules. In terms of whether you do it in joules or kilojoules, depends on how big your numbers are. Like this number is really big, so I'm going to make everything into kilojoules. If it had been the case that this number is really small, I might have taken everything to joules. 16.5 kilojoules. And so my Q total (113 plus 16.5). It's addition, so I can only keep to the ones place. 130 kilojoules to get the job done. The most important piece of advice I have for you working these problems is always draw the heating cooling curve. If you don't draw the heating cooling curve, you miss things. You just see 21 degrees, 100 degrees, and you end up only doing this part of it, when the vast majority of the energy actually came from the part where you had to vaporize it. So don't try to do this without sketching a heating cooling curve first. It's very easy to forget steps if you try to skip the heating cooling curve. Number 3, How much energy would you need to remove from 15 grams of water at 15 degrees to turn it into an ice cube at -5? First things first, draw a heating cooling curve. I'm at 15 degrees Celsius. So that's maybe right there. I want to be ice at -5. So I have to cool it down. I have to freeze it, which is to come across this plateau, and cool it down some more to end right there. That's energy being removed. Every single one of my Q's is going to have to be negative because energy is flowing out. So I'm starting with a not very warm liquid, so a little bit in the thermal account and 2 bars in the phase account. I'm finishing with less energy in my thermal account and less energy in my phase account. So we've got an overall outflow of energy. 3 segments requires 3 physical constants and three calculations. So this is going to be specific heat for the water. This is going to be delta H of fusion. And this is going to be specific heat of ice. 4.184 joules per gram degree Celsius. Heat of fusion, checking my sheet, 6.02 kilojoules per mole. And specific heat of ice, 2.11 joules per gram degree Celsius. So I found all my parts and pieces. I'm ready to calculate. I've got a piece that's going to be energy given up by the water, which will be specific heat of water, times the mass, times the delta T, but only for the time frame that we're in the liquid phase. I've got Q freeze, and this is the one where we have to control the sign. I'm going to have to remove energy equivalent to the number of moles I have times the heat of fusion. I didn't have to install the negative sign out here in the Q for the water because the delta T is going to take care of that for me. And then I have to remove some energy from the ice once it's frozen, which will be the specific heat for the ice, times the mass, times the delta T for the time frame during which it's ice. 3 segments, 3 equations. Here we go. 4.184 joules per gram degree Celsius times the mass of the water, 15.0 grams, times the change in temperature during the time that it is water. So from 15 just down to 0, coming down by 15.0 degrees Celsius. So coming down that first segment, 4.184 times 15 times a negative 15, we must remove, which is the negative sign. Keep 3 sig figs here. 941 joules worth of energy to cool down the water. To freeze it, so we again have to do the moles thing. .015 grams in a mole. 15 grams divided by 18.015. We've got a little less than a mole this time. which means that I have to remove 6.02 kilojoules to freeze 1 mole. Since I have a little less than a mole, I will remove a little less than 6.02 kilojoules. So I have to downscale. Heat of fusion, 6.02 kilojoules per mole. Moles cancel. Up here we have the grams cancel and the degrees Celsius cancel. 0.833 times 6.02 . 5.01 kilojoules removed because I want to freeze it. And then I have to cool off the ice once it's frozen. Specific heat of ice is 2.11 joules per gram degrees Celsius. My ice cube weighs the same as what the water weighed. And while it is ice, it only drops in temperature by 5 degrees Celsius. So that 20-degree temperature change got split into 2 segments. 2.11 times 15 times -5. We can only keep 2 significant figures here because of the 5.0. So I'm going to lose 160 joules. Again, I'm going to have to add that all up to get my Q total. So we got to put it all into the same unit system. So this is negative 0.941 kilojoules. That's in kilojoules already. And this is negative 0.16 kilojoules. Looks like I can keep 2 decimal places when all is said and done. 0.941, 5.01, 0.16, all of that being negative. And in the end, I'm going to have to remove. So I've got to keep our negative sign. I must remove 6.11 kilojoules worth of energy to travel all of that. So that is how we solve heating cooling problems. Now, we really have, at this point, 2 separate types of problem. I want to make some clarifications here between the 2 separate types. We have 2 types of problems here. We have energy exchange problems. That is like you put everything in a styrofoam cup, you let it all come to the same temperature, and the energy gets traded around. And so we've got one thing, and we have another thing, and we're basically pushing the energy from one thing to another thing. And the energy that comes out of one of them has to go into the other one, such that the total energies, however many parts and pieces you have, add up to be the same. And it takes one of these little LOL diagrams to describe each piece of the system to calculate how much energy was involved in that. These were the kind of problems we were doing as part of that specifics of temperature change activity. Once we met the ice, we figured out we actually had another situation, and that was, what if something was heating and cooling and perhaps changing phase? A heating and cooling problem only deals with one substance, like our icy hot demo. We just looked at how much energy got moved into the ice cubes as we took them from ice cubes all the way up to boiling. We didn't actually worry about the energy that came out of the hot plate. So this is one single substance traveling along some kind of a journey here, and you have to string together all the different parts and pieces for the parts and pieces that are involved here. So the very first question to ask yourself when you're dealing with these thermal energy problems is, what kind of problem? What kind of problem do I actually have here? Am I exchanging energy, in which case I want to make all the Q's add up to 0, or do I have just one substance that's being either heated or cooled, in which case I have to look at every single segment and add up the parts and pieces for each and every segment. Your homework assignment for tonight is to go back to Learning Target 2.2 and do letter B. Okay. Letter C was the calorimetry style problems, the energy exchange problems, and you did those. This 2.2 is more of the style problems we were working today, the heating cooling problems. For the next part of this, we are going to look at the other thing you picked up from me, which is this enthalpy of packet. This starts out as a reading assignment, and I'm going to give you a chance to do some of the reading here. These heats of fusion and heats of vaporization can also be called enthalpy of fusion and enthalpy of vaporization. Enthalpy is a word that seems to cause a fair amount of just general confusion. And so instead of having you read the textbook, I wrote some stuff that kind of uses some of the language that we have used to get ourselves to where we want to get. I want you to start by reading up to this point right here. And then we're actually going to get out the model kits and we're going to build this little reaction. So read up to where it says, here's a look at what has to happen as the reaction to form water occurs. Let's have a little quiet reading time here.